Thank you again for the introduction, and thank you all for coming again. Oh, I have to wait. Okay. You're seeing the screen, right? Okay. Here. So today I'll go a little deeper into the proof. So I will first review the HHL formula, and I will introduce the notion of field diagram, which is a little more general than the usual partitions, and its McDonald polynomial. And then I will introduce what we call column exchange rule, which is very the key of the proof. And if time permits, I will give you some remarks about column exchange rule. And I think I have to prove the column exchange rule in the next lecture, so next week. So I will first review the HHL formula. So I think everybody in here knows, but anyway, for a subset of n-1, say the quasi-symmetric function, fundamental quasi-symmetric function, or Gessel's quasi-symmetric function, f of ns, or we can just write fs if what n is clear in the context, is defined by the sum of monomials xi1 through xin, where i1 and i1 through in are weakly increasing, and okay, if j is in S, then ij is less than ij plus 1. So this is what fundamental quasi-symmetric function is. And Hageland-Heyman-Lohr formula is a formula for the fundamental quasi-symmetric function expansion of the modified McDonald polynomial. So to recall their formula, I have to recall some preliminaries. So if you have a partition like this, and if you have a cell here, then the number of cells in the same row and right to the given cell is called arm. And this is called leg. This is called co-arm. And this length is called co-leg. Okay. And for a partition mu, a pair U and V of cells in mu, they will call is a tacking pair if either of these two conditions satisfied. So either U and V are in the same row and U is left to the V, or U is in the row right above the row where V is, and U is right to V. So if these two conditions, either of these two conditions satisfies that, then we call the pair U and V is an attacking pair. And for a filling, so we fill numbers in the cells of a partition. So filling sigma of mu, a pair UV of cells we say it forms an invergent pair if U and V, UV is an attacking pair. And the filling of U is larger than the filling of V. And then we will denote the set of inversion pairs. Inversion pairs of sigma by inv mu of sigma. And we'll define the inv mu of sigma by the product of Q, where the product is over all inversion pairs. So the definition is slightly different. In mu usually counts the number of inversion, but we decided to slightly modify the definition. And this is not very big difference. So, and so I will give you an example. So for example, I will take our partition to be 331. And our filling to be something like this. And in 331, I'll just in mu. And sometimes we will write this filling as a permutation because we already have partition here. So by reading this filling in the reading order, so from left to right, starting from the first row, starting from the top row to the bottom row. So it's 3, 2, 5, 7, 6, 1, 4. And I have to count the inversion pairs. So this one is an inversion pair. The attacking pair in the second type. And these two forms an inversion pair, where attacking pair is of the first type. So there are 3 inversion pairs, and the inverse statistic is Q to the third. Okay. And once again, for a filling sigma of mu, we say a cell U is a descent of sigma if sigma U is larger than sigma V, where V is the cell right below U. So U and V are placed like this. And denote the set of descents of sigma by this mu of sigma, and define our major match statistic, match mu of sigma, by product of q to the minus arm times t to the leg plus 1 over all descents. Okay. So, and for example, I'll just copy and paste this one. So for this same example, the match mu, we have to find descent. So since 3 is bigger than 2, this cell is a descent. This cell and this cell, these are the descents. And q to the minus arm, t to the leg plus 1 is t here, q inverse t here, and t. So match mu, or match mu of 3, 2, 5, 7, 6, 1, 4 is q inverse t third. And finally, we will define the stat mu of sigma to be the product of inv mu and match mu. So inv mu sigma times match mu of sigma. And in our example, remember that inv mu was q to the third. So it's q squared t cubed. Okay. And the celebrated
question here.
Yeah.
If you slide your page a little.
Oh yeah.
Yeah, thank you. Do you have a concept of hooks in this case? Because if you say arm plus leg plus 1, that's hook length in general, in the partition situation, right?
Yeah.
So which means in this case, I wonder what you get if you, as last time, if you change Q into 1 over T, then you're adding those. So do you get anything? Hook statistics?
Yeah, but I'm not sure what we can say about those kind of statistic in the combinatorics of McDonald polynomial. Yeah. I know. Okay. Yeah.
Okay.
Yeah. Thank you for the question. And the HHL formula or theorem of Hegel, Heyman, and Lohr in 2005 is for a partition mu. We can write the modified McDonald polynomial as a generating function of step mu of sigma times f of inverse descent of sigma over all permutation sigma of n. So I will give you an example, so small example. So for example, if we take mu to be 2, 1, then our sigma is 1, 2, 3, 1, 3, 2, 2, 1, 3, 2, 3, 1, 3, 1, 2, 3, 2, 1. Okay. I write it this way because the inverse descent of sigma is the empty set 1, we have 2, and we have 1, 2. And we can count the inv mu, match mu, and then we obtain stat mu as a product of these two. So for inv, we have to find the inversion pairs. So inversion pair can only occur in these two. So this one, and this one. So inv mu is 1, 1, q, q, 1, and q. And match mu, we have to find the descent first. And descent can only occur in this position. So this one is descent, this one, and this one. They are all descents. And the q to the minus arm, t to the leg plus 1 always give t. So 1, t, 1, 1, t, 1. So stat should be 1, tq, qt, and sorry, it's t. It's qt. So the HHL formula says that the modified McDonald polynomial of 2, 1 is f empty set plus q plus t times f1 plus q plus t times f2 and qt times f12. And if you are familiar with the computation of these kind of stuff, then you will see that this one is S3. So it's q plus t times S21 plus S111. Sorry, qt times S111. So this was, we have calculated in the last lecture. So HHL formula does give the right formula. And our purpose was to compute the McDonald intersection polynomial. Our goal is to compute the McDonald intersection polynomial I lambda mu, which was defined by the divided difference. So t lambda times h tilde mu minus t mu times h tilde lambda and T lambda minus T over T lambda minus T mu. And I didn't give you the remark that this is symmetric of lambda and mu, so you don't have to worry about the ordering because it's intersection, so it should be symmetric with lambda and mu. Anyway, we want to compute this one, and if we are living in our dream, so we may hope the HHL formula just gives the right calculation. So what I mean by is that that for any sigma in for each sigma in permutation sigma, it satisfies sigma. I mean, we have either stat mu of sigma and stat lambda of sigma are the same, or if we multiply T lambda to the stat mu and T mu to the stat lambda, and then they are equal. So if we have this situation, then the I lambda mu, if the permutation satisfies the first one, then we are doing nothing here. So we once again we obtain stat lambda. And if the permutation satisfies the second condition, then the term indexed by the sigma vanishes because we have multiplied T lambda and T mu and then subtract. So I lambda mu is a generating function of the same stuff over our permutation, where sigma it satisfies the condition number 1. Okay, but unfortunately, it's not the case. Yeah, it's fortunate for us in a sense because there's a problem we have to solve. So it's not trivial. So I will give you an example. So I'll just copy and paste this one. Okay. So, and I will erase this. Okay. And I will write the permutation like this. Okay. And stat mu. So mu, okay. So, for example, mu is 2, 1, and lambda is 3. So we have computed stat mu. So right now I'm going to compute stat lambda. The inverse distance should be same. So, and the stat lambda, if you think of it, there's no descent here in the partition 3. So all you have to carry is an inversion. And the inversion statistic in this particular partition is just an inversion, user inversion statistic. So it's easy to calculate. So I'll just give you the answer. 1 Q square, Q square, Q. And if you see this data, you can see that these two satisfy the first condition. These two satisfies the first condition. These two and these two satisfies the second condition. So their ratio is T lambda over T mu. But these two or these two satisfies none of it. They are not the same, or their ratio is strange. But fortunately, you can observe that these two satisfies the second condition. So the ratio of it is T over Q to Q square, which is T mu over T lambda. And these two are the same. So these two satisfies the first condition. So the natural question arises is, can we swap this? So and we modify the combinatorial formula, the HHL formula, for these two modified Macdonald polynomial H mu and H lambda to somehow swap the stat properly. So these were this is the question we had.
Question.
Yeah.
But before you take up this project, is it true that you can always find such pairs, so to say, for any permutation in partitions?
But the question is,
okay, I'll repeat. In this example that you drew with the red and the blue,
blue.
Initially they were not working out by satisfying conditions 1 and 2, but you modified and it worked.
Yeah.
Is it always possible to do so?
Yeah.
Okay.
And that's how we proved. I mean, we introduced the way how you can swap these and find these pairs.
And is there a canonical way of doing this, or is there an algorithm?
We don't think, I mean, there's no canonical way because the pairing is not unique, so to speak, but yeah, but we believe our proof is very natural. I mean, you will see in the next lecture. I mean, if you see the proof, it feels like it's the only way to prove. I mean, but I'm not gonna say it's canonical or natural in a sense.
Yeah. Thank you.
Okay, so to explain how what is swapping means, I have to define some notion. So a diagram, and we will use D for the diagrams, is a collection of cells. So a partition is a diagram. So it's just a collection of cells. And a field diagram is a pair D, pair D and F, where D of diagram D and a filling function F, which is defined on the diagram, but some technical reason we will exclude the bottom cells of D to some given field F. So where F is a field. And for our purpose, it usually contains the field of rational function over Q and T. But but you can think of it as general as possible. So any field. And for a filling sigma of D, you can define the inv D and dis D, inv D and distant set of D in a very similar way, similarly to inv mu and dis mu. It's quite the same. But the match mu is different. So match of the field diagram, df of sigma, but it's almost the same. Remember the match mu, we had a product of q to the minus arm, t to the leg plus 1. We just replaced the monomial, q to the minus arm, t to the leg plus 1 with the value of filling function. So F over all descent of sigma. And once again, we will define stat df of sigma by product of inv and match of sigma, okay? And finally, mimicking the HHL formula, we define the Macdonald polynomial. It's a generalization, but we will not mention it always. I'll just mention it as modified Macdonald polynomial. Modified Macdonald polynomial H tilde df is defined as a generating function. So H tilde df is a generating function of this stat times F inverse descent of sigma over all permutation sigma. So it's very clear that if we let our diagram to be the partition mu or partition mu and our filling F mu standard, the standard filling is defined by Q to the minus arm, T to the leg plus 1. If we set our diagram and filling in this way, then the HHL formula implies that this df is the same as the usual modified Macdonald polynomial. Okay, so for example, and we will draw our field diagram by drawing a diagram and then put the filling function, the value of the filling function to the cell. So let's just say the value of filling function of this cell is alpha. And we didn't define the filling function for the bottom cells. And yeah, once again, we can calculate okay, for these permutations, the inv d of sigma counts the inversion pair. So here,
I think
here.
you have to arrange the last three.
Yeah. Yeah, sorry. Oh, sorry. Okay. And here, these two are inversion pairs. So it will give 1 q, and q square. And oh yeah, and inverse descent was empty set 1, 2, and 1, 2. And the match d of sigma. Match df of sigma. We have to find the descent, and descent only occur in this position. So this one, and this one. So it's 1, 1, alpha, 1, alpha, and alpha. So the stat df of sigma is 1 q alpha, q alpha, and q square alpha. And finally, we can compute the Macdonald polynomial by f empty set q plus q alpha times f1, q plus q alpha times f2, q square alpha times f12. Okay. And I would like to give you a remark. There were some study in the literature where they studied generalization of Macdonald polynomial to a general diagram. So, for example, Bergeron, Garcia, Heyman, Tesler, they studied some Macdonald polynomial of lattice diagram, and Bandelow, he studied modified McDonald polynomial for general diagram. And our definition is different from the first one and slightly generalized the second one. And the remark I really like to make is that our definition is essentially same as the weighted characteristic polynomial of Carson and Mellett. In their paper, they proved the shuffle conjecture with this df. So what I mean by this is they defined they defined a weight. Okay, so for a thick path pi, weight is a function defined for the corners of pi, and for a weighted thick path pi and weight, they define this characteristic polynomial as a generating function of product of Q over cells in pi, such that sigma I is larger than sigma j, and product of the weight of corners, where C I comma j is in the corners of pi, and sigma I is larger than sigma j, and then inverse descent of sigma over all permutation sigma. And what I'm saying here is that there's a way to associate the weighted thick path pi weight to each field diagram df. So we can associate a pair of pi, thick path pi and the weight function for each field diagram, so that we have the modified McDonald polynomial of df is the same as the characteristic polynomial of pi and weight. So yeah, this is one remark I'd like to mention. So far, so good. Okay, if there's no question, yeah, and since we have generalized the modified McDonald polynomial, we may want to find some relations between the modified McDonald polynomial for field diagrams. So by relation, I mean, so it is possible that for two distinct field diagrams, df and d prime f prime, and they have same McDonald polynomial, d prime and f prime. So this is somehow good because we wanted to swap the stats. So we can make starting from one field diagram, and we can somehow change the field diagram, but still have a same McDonald polynomial. So I'll give you an example. So mu is 2, 1, lambda is 3. So mu and the standard statistic gives this field diagram. Q to the minus arm and T to the leg plus 1 is T. And lambda of F lambda standard is this one. There is no filling function. And we will define D and F to be this field diagram, Q inverse and T. Yeah. Then you can calculate if you remember, Hold on one sec. We have failed to pair the same permutations for the stat of this one and this one. So stat mu f, mu f mu standard of sigma, stat mu f mu, lambda f lambda standard of sigma was, oh yeah, we have calculated this one, right? So we failed to pair all these satisfying the condition 1 and 2. But if we take the stat of D and F of sigma, so it's 1, and if you put 2, 1, 3, there is no inversion pair. Oh, no, there is one inversion pair here, and there is no descent, so this gives Q. And 2, 3, 1, there is one inversion pair and one descent, so Q times Q inverse T, so it gives T. And if you calculate all these, you will obtain this one, QT. Oh, sorry, so it's QT, okay. Okay, and you will see that the sum of all these are the same as the sum of all these. So these two are the same. So we have different field diagram, but they have same Macdonald polynomial. Moreover, somehow these two statistics swapped in this new one. So for this new field diagram, we have these three satisfying the first condition where the stat is equal, and these three pairs satisfies the second condition. So these three pairs satisfying their ratio is T lambda over T mu. So in some sense, we have computed the Macdonald intersection polynomial in this way. And from now on, I'm gonna introduce some relations, such relations, like the two distinct field diagram with same Macdonald polynomial. So first relation is what we call the cycling lemma, and it's very easy. It's obvious from the definition. So cycling lemma, I'll just give you an example. So cycling lemma is something like, if you have a field diagram like this, so, and filling function A, B, C, D, then you can send this first column to all the way to the right, but you place it one up. So you have CD, and you have the first column in the one place up, so A and B. And if you remember the definition of inversion pair, inversion pair and the match statistic, then you can see that these two gives the same Macdonald polynomial. Okay, cycling rule is easy one. And the second one I'm gonna introduce is what we call the column exchange rule. Oh yeah, and if you see this example, so from the field diagram, the first field diagram to the second field diagram, we kind of exchange these two columns, right? It was of shape 2, 1, but we kind of exchange it. And there's some difference with the filling function. And we observe this, and we have generalized this in a very general setting. So proposition, if our field diagram mu f mu, yeah.
I think you did some kind of a straightening by switching columns from the first to the second to get identifications. Now, is it enough to get this identification or straightening, always by switching one column alone?
No, we have to. I'll give you an example after I introduce the column exchange rule. Yeah. Column exchange rule is a local rule that can exchange two columns with under certain conditions, and we have to apply column exchange rule iteratively. Then we can somehow obtain this kind of situation. So some pairs satisfies the condition one, and some pairs satisfies the condition two. But I'll show you how we do
Okay.
later. So the first field diagram mu f mu is of the form like this. So first column is of length n, and the second column is of length m, and the filling is given by b1 bn minus m minus 1 and q alpha, so it's q alpha, and alpha a1 alpha a m minus 1 a m minus 1. And the second field diagram, lambda f lambda, is a field diagram which is obtained by swapping these two columns. Okay, but you have to erase this q. Okay, so it was happened in here too. So the filling function was, the value was t here, but when we swap these columns, the filling function became q inverse t. So it somehow erased one q. Okay, and then there is stat, inverse descent, and content preserving bijection. There's a I will denote the bijection by phi and m from the permutation of n plus m to Sn plus m. Okay, and in other words, the bijection phi and m satisfies. What is the stat inverse descent content preserving means? So it satisfies the phi1 stat mu f mu of sigma is the same as stat lambda f lambda of phi and m sigma. And we get the same thing for inverse descent. So phi2 is inverse descent of sigma is inverse descent of phi and m sigma. And the final condition, phi3, is phi and m is content preserving. What they mean is we don't send a filling here to any other rows. So we kind of preserve the filling in the row. So sigma I is same as phi and m sigma of I. Oh, it's the same. We don't have to care about the same. For I starting from n minus m, okay, 1 through n minus m, and sigma n minus m plus 2i minus 1, sigma n minus m plus 2i is the same as the set of phi n m sigma of n minus m plus 2i minus 1, comma sigma n m sigma of n minus m plus 2i. Okay. For I from 0, sorry, n minus m, I from 1 to m. Okay.
By the way, in this third condition, part 2, they are equal as sets. They're not equal as individuals, or it means you can swap the equality, right? Between, you have one pair equal to the other pair as a set.
Can you say it again?
Okay, let me say this again. In this condition, phi 3, the second part, you have one set equal to another set, right?
Oh, yeah.
And that, are you saying that sigma of n minus m plus 2i minus 1 equals one of the two on the right-hand side?
Yeah.
One of the
Yeah.
two.
Yeah.
Okay.
So basically we, okay, this, I think this makes more difficult. What I'm saying is if our filling was 1, 3, then the bijection send it to 1, 3 or 3, 1. So these are all cases. So we may swap these two numbers in a row, or we just leave it. Okay, that's what the third condition saying about.
Thank you.
Okay. Okay. So one thing you may have noticed is that okay, I should write it here. So the condition phi1 and phi2 implies that we have the field diagram, modified Macdonald polynomial of mu f mu is the same with the modified Macdonald polynomial lambda f lambda. Because we have step and inverse descent preserving bijection, and these are the generating function of that. But we really need phi3 in when we are applying it to the Macdonald intersection polynomial. And one more thing I would like to remark is that, okay. Yeah, these are one remark. And I will give you the example as okay, so starting from a partition 5, 4, 3, 1 with the standard filling. So f mu is f mu standard. And our mu f mu is t. I'll just write it down. T3 T Q inverse T minus 2T third. Oh, sorry. Oh. Okay. T Q is 2T2 and T. Okay.
I think you missed one square, no, or not? You missed one square.
Oh, hold on a sec.
And the third one, I think.
No? Yeah. I think it's 5, 4, 2, 1. Yeah. Thank you. Yeah, this is what I want to calculate. Yeah, the partition is 5, 4, 2, 1. And you can see that when you see these two columns, you see T here. So our alpha is Q inverse T because this is Q alpha. And these, this is A1 and this is alpha times A1. Okay. And this is A2 and this is alpha times A2. So So these two columns satisfies the column exchange rule. So we can apply column exchange rule to obtain this field diagram. So we can exchange these two columns and change the stat by Q inverse T, change the filling. And we can also apply the column exchange rule for these two to obtain this new field diagram, Q inverse time T. And then by applying the cycling rule to send the first column to the all the way to the right, and then place it one row up, we obtain this field diagram. Okay. And we take our lambda to be 5332 and f lambda to be f lambda of standard. And lambda f lambda standard is okay. This one, and I'll just fill. I'll just write the fillings. Q inverse T squared. T squared. Q minus 1 T. Okay. And we can apply the column exchange rule for these two columns. So eventually I'll apply column exchange rule all the way to the left to send this fourth column all the way to the left. So this will give this field diagram with the filling changed by Q inverse. And we can apply the column exchange rule once again to these two. So to obtain a field diagram like this. And again, we obtain the field diagram like this. And then we apply the column exchange rule to this column all the way to the right. So once again, our alpha is Q inverse T, and you can see that you can obtain the filling of the third column by multiplying alpha to the second column. I mean fourth column. So that's why we can apply the column exchange rule. And this will give us okay. This will give us something like this. And then applying column exchange rule once again, then we obtain a field diagram like this. And finally, we apply the cycling rule to send this first column to the last column and place it one row up. Okay. And then, I will just copy and paste the final ones. So this field diagram DF is obtained from the field diagram mu, and this field diagram D prime F prime is obtained from the field diagram O. I think I made a mistake. Oh, I think I have made a mistake. Yeah. Oh, I'm screwed. I think I have to send this column here and send this column here. And I think I screwed. I mean, what I should obtain is these three columns are the same, but these two are different. So sorry for, I'll make a note. I made a mistake, and somehow there's a way to apply column exchange rule, which is very similar what I did, but I did it wrong. But the result is we have these three columns are the same, and these two column is the only thing we have to focus. So that's what I was gonna do, but yeah. I sorry for the mistake, and I got no time to make it right. So this is all I have for today. And for the next week, I will give you the proof of column exchange rule. And sorry for the mistake, and I will upload my notes with the corrected one. Okay. Thank you for listening.
Okay, well, let's thank Jaeseong. And no worries about the mistake. I did a lot of examples myself and verified you can do this.
Yeah.
So yeah, just fix it in the notes. That'll be fine.
Yeah.
Oh, any questions?
Yeah. Before I get the question, I have to mention one thing. So, what we have obtained, like the equation is the same as modified Macdonald polynomial of df. This equation was obtained by Hagelin, Heyman, and Bloor in their paper where they studied the non-symmetric Macdonald polynomial, and they gave a proof uh, by certifying some defining relations. I mean, triangularity and the normalization conditions for the Macdonald polynomial. But and our proof is bijective. So our proof provides a bijective proof of their result. Yeah, that's the remark I wanted to mention. Yeah. And what was the question?
Was there a question?
Brendan?
Well, I guess I have a question.
Okay.
So we have these kind of new diagram labeled Macdonald polynomials, and I understand that you're kind of interested in when they're the old Macdonald polynomials. But do you get sort of new, interesting, sure positive symmetric functions this way?
Oh, in a sense, it's always sure positive because if you see the definition, you can realize that the new modified Macdonald polynomial is just the sum of ribbon LLTs as a HHS formula. So sure positivity follows by that.
Well, and I guess maybe a follow-up then. So the only way that we really know the LLTs are sure positive is from Kastadt-Lustig theory.
Yeah.
It's this kind of very indirect thing about Kastadt-Lustig polynomials ultimately having non-negative coefficients. But when you look at a Macdonald polynomial, we have a representation theoretic model. Is there any hope of getting representation theoretic models or some way of not just saying Kastadt-Lustig theory? Or some, at least, maybe not all, but.
That's a very interesting question, but I'm not hoping it right now because I mean the statistics for Macdonald polynomials were very natural things to consider, like image statistic, and our field diagram is kind of arbitrary. So, but for that question, we may want to find some new natural way to, natural statistics, natural field diagram or natural weighted dict path in the words of Carson and Mellon.
Okay.
To give a representation theoretic model.
Cool.
Any other questions? Okay. I'll thank Jaeseong again, and good night or good morning to everyone, depending on where you are. And we'll see you on Tuesday next week for lecture 3.
Yeah. Thank you.
So,
Bye, everyone.
Bye.
Great talk.
And Jim, I had a question
oh, okay.
about, I mean,